So when are we rolling?
I think we're rolling now. There'll be a 30-second delay there. So we should just start talking.
Okay.
Hello, my name's Daniel Mansfield, and I'm joined here with Daniel Chan.
Hi.
Hi, Daniel.
So this is the first algebra test review. So
yeah, that's pretty much all there is to the introduction. We're going to go through the questions as before in the previous one. We'll just alternate. Daniel's got the first one, I've got the second one, and Daniel will do his answer. I'll come along and say what I like about it, and we'll talk about what you could do perhaps differently. The idea is to do it in the exam style, although Daniel and I will somehow we'll usually resort to trying to teach people things, but we're going to try and do it in the exam style.
we'll try to make sure you know how to approach the question when you're in a test situation. So that's probably the key thing.
Yeah, and so please enjoy. I'll monitor the chat while Daniel does his thing, and then I'll come back.
Okay, great. Okay, so in this first question here, it's written here, question 1. We're looking at 3 points in R3. So it's A with this coordinates, B with this coordinates, and C with this coordinates. And the first part of this question asks us to look at the parametric vector equation of the straight line AB. That involves these 2 points. And then the second part is to see whether this point C actually lies on that straight line as well. Okay, so this is a question that's testing your understanding of parametric vector equations for lines. So let's just remind ourselves what the parametric form is. So it's x equals a plus lambda b. And all you have to do is remember what the a and the b represent here. Okay, so always have a good picture in mind when you're doing any of these questions. Okay, so remember that a represents the coordinate vector for a point on that line, and the v represents a direction. So in this case here, you can pick for the point, coordinates of the point on the line for A. You just have either of these 2 points, it's the line AB. So you can put 4, 2, 3. And for the direction, I guess you have both A and B on it, so that can be an A, that can be a B. And you just look at the displacement vector from A to B. Okay, so that's easy enough. B equals the displacement vector A to B. And of course, how do you compute that? Well, you just look at the difference of the coordinate vectors of B and A. Okay. 5 minus 7 minus 2 is the coordinates of B. And you just have to subtract the coordinates of A. Minus 4, 2, and 3. Okay, so let's see what that is. Remember, just have to subtract coordinate-wise. 5 minus 4 gives you 1. Minus 7 minus 2 gives you minus 9. And minus 2 minus 3 gives you minus 5. Okay, so you have the 2 parts that you need to do to put into this parametric form. I lost the fact. You should also write what is lambda. Okay, lambda ranges over all the reals, so make sure you put that in there. And now you just have to substitute these 2 values into this form here. Okay, so part 1, the answer here is x equals 4, 2, 3 plus lambda times 1 minus 9, this is the v here, minus 5. Okay, and lambda ranges over all the reals. Okay, so to do part 2, okay, we're asked to see if C is on this line. Okay, that's part 2. And so I guess it's a yes/no answer. Let's see which one of the 2 it is. So remember what this means, this parametric form. It means that as you vary lambda, you sweep out all the points on this line. Okay, so if you think of lambda as a time parameter, it's a trajectory of some point inside space here. Okay, so basically you want to say, does C lie on this line means that, does it have this form? Okay, so we're just going to solve for the coordinates of C. So we're going to solve. Let's see how much space I've got. 7 minus 25 minus 10 equals this part here. 4, 2, 3 plus lambda 1 minus 9 minus 5. Okay, so we want to see whether you can solve this. If you can solve it, you can find this lambda, so it lies on this line. And as usual, you try to get lambda by itself. So we'll put this over to the other side. Let's subtract 4, 2, 3 from both sides. Okay, so let's just add a little bit here.
We could wipe some stuff out.
Okay, I think we can go here.
Okay.
I think that's fine. Okay, so let's just subtract 4, 2, and 3 from both sides. So it cancels with that. So 4 from here leaves you 3. 2 from here gives you minus 27. 3 from here gives you minus 13. And that equals lambda 1 minus 9 minus 5. And can you solve for such a lambda? Well, the thing is that for the first coordinates to be equal on both sides, you need lambda equal to what? So first coordinate implies that 3 equals 1 times lambda. Okay? And for the second coordinate, then for lambda equals 3, 3 times minus 9 is minus 27, which is fine. But for the last coordinate, if you put in lambda equals 3, you get 3 times minus 5, which is not minus 13. So, but minus 13 doesn't equal this lambda times minus 5. So 3 times minus 5. So therefore, you can't solve for this lambda. Okay? Therefore, no solution. And if there's no solution, that means that it's not on this line. So C is not on this line. Okay, so remember at the end of this question, always answer the original question. You've done a lot of solving. Okay, but don't forget, at the end of the day, you want to say, is it on the line? And here, the answer is it's not on the line.
Cool. I like this answer. The thing I particularly like about the answer is that Daniel's got a picture here, which will help him to kind of string together all these algebras and vectors and sums and things. So I really like that. I really recommend this. This is a great idea. It'll help you answer the question. Aside from that, yeah, it looks good. Looks very nice. Typically, what you want to do when you're asked, even back in high school, when you're asked, is something on a line? What you would do then is just sub it into the line and try and solve it. And that's exactly what's happening here. There's nothing new here. You just have to try and solve for lambda, and in this case, there's no possible value of lambda. Lambda is simultaneously 3 and what is it? 13/5. It can't be both those things. All right. Cool. All right. Next question.
Okay.
Okay. My question is, find parametric vector form or the plane given by this equation. So this is Cartesian form. It's given as a restriction on the x1, x2, and x3 coordinates. And in order to convert this into parametric vector form, what you need to do is introduce some lambdas. So there's three variables here. If I choose a value for x1, and I choose a value of x2, that's going to determine for me my value of x3. And in this way, I'm going to choose my parameterization for the plane. I'm going to let x1 be a parameter, I'm going to let x2 be a parameter, and then I'm going to write everything in terms of these two parameters. And So here are my variables x1, x2, and x3, all written in terms of my parameterization with lambda 1 and lambda 2. Hence the plane in parametric vector form. The plane is given by x is equal to, well, what is my x1, x2, and x3? x1 is just lambda 1. x2 is just lambda 2. And x3 is this. Which I can write as a sum of a constant vector, a vector which is a multiple of lambda 1, and a vector which is a multiple of lambda 2. Good. My Cartesian equation, sorry, my parametric vector form of the equation of the plane. And hence we're asked to give two non-parallel, non-zero vectors which are parallel to the plane. So there's a lot of words. There's a lot of words in this. What does it mean? Well, the plane, I'll just draw a kind of picture for you like this. Here's the point 007, and here's my two directions like this, going in the plane. Now, the vectors which are not parallel, that means not parallel to each other, and not zero, which means the vectors can't be zero, which are parallel to the plane, are these two vectors. This question is just asking you for the directions of the plane. It's asking you to just write down which of these things are the directions. So that's the kind of informal description of it. The vectors which are parallel to the plane are technically the ones that are in the span of these two things. Anything in the span of those two vectors is said to be parallel to the plane. Maybe I need more space for this. And if I'm asked to pick two vectors out of here which are not parallel and not zero, then I'll choose that one and that one. Thank you very much. Good.
Great. Great. That's a great solution, Daniel. So yes.
Thank you, Daniel.
So so the key things, of course, we would look for is for you to write this x in parametric form, so it's in terms of the two parameters, and of course then once it's in this form, it's pretty easy just to pull out two vectors which are not parallel and are in the parallel to the plane. So what happens if instead of x1 and x2 you picked x2 and x3, Daniel?
Well, I get a different equation, different but equivalent parametric vector equation for the plane. Now, I cheated a little bit here. Well, I knew what was going to happen. If I take that one as my first parameter and that one as my second parameter, it's really easy to isolate that parameter because it has no coefficient. So I deliberately chose that one for a parameter and that one for a parameter just to make life easy for myself and avoid fractions. But you would get a different equation of the plane. So there's many actually answers to this question. And one thing you might have noticed is when you're doing these questions at home, your answer is not the same as the answer in the book, which is frustrating because potentially both are correct. So one thing you can do is check your answers, and this is a kind of thing you can do at home when you're doing your questions, or you can do it in the exam as well, because it's really easy to check your answers. For example, this point here, does this correspond to a point on the plane? Well, take the point with coordinates 0, 0, 7 and sub it back in to the equation. 0 minus 0 plus 7 equals 7. That's good news. What about the directions,
Looks good.
Daniel?
Yeah, so the other thing is, so we know this part looks correct, so what about these two directions? I guess if we want the directions to be correct, the easiest thing to note in this case is that we're looking at a plane in R3. It's given by this Cartesian equation, and the good thing is that this is very close to the point normal form, so you actually can read off straight away what a normal to this is. So the normal is actually just given by the coefficients of x1, x2, and x3. So let's put that down. I think I've got...
Maybe we can remove some of the top.
Yeah, we'll get rid of some of the top. And then we'll see
Whether I'm right.
Daniel's made a mistake in the calculation. It's very easy to do, so do check your answers. Okay, so what's the normal here? It's just equal to 2 minus 5, 1. 2 minus 5, 1. So what does normal mean? What is it normal? It's normal to the directions of the plane. So presumably this one and this one, if they're calculated correctly. So to be perpendicular, how can we check that they're perpendicular? I guess you just check the dot product is 0. So that's what we'll do. So let's check. Check 0 equals n dot 1, 0 minus 2. 1, 0 minus 2. So that's 2 minus 5, 1 dot 1, 0 minus 2. So let's see what that is. So I guess you multiply corresponding terms. 2 times 1 is 2, plus 0 minus 2. It's looking good, Daniel.
I'm just going to move the camera
And then, okay, if you do that, and I guess the other one you should check is 0, 1, and 5. So let's check. So this is okay. Okay. So the other thing is 0 equals, so what's our normal? 2 minus 5. So this is the thing we're checking, so I'll put a question mark because we don't have to know whether that's true yet. 2 minus 5, 1. Dot 1, 0, 1, 5. So what's that equal to? 0 minus 5 plus 5 equals 0. Okay? So in this situation, the way you would write it out, you can leave that out first. You just leave that out. Okay? And then you just say that this is equal to 0. So this is indeed normal, perpendicular to this normal. Okay?
Awesome. And when I'm marking these tests, there's all sorts of answers, so I actually have to go through this computation myself, and I really like it when a student's done the calculation for me. This is so lovely, because it saves me the trouble of going through and checking the calculation. So it's really good that we're all on the same page, and we all know that this is a form, a parametric vector form of the plane. Good.
Okay. Yeah, so just one final thing. As with all these questions, lots and lots of different ways of doing it. The idea here is you want to introduce some parameters, you put them in, but of course the other thing is you can just pick 3 points on this plane. Okay, that's another easy way to do it. And once you have 3 points, you've got at least 1 point, which you can put in here, and to get the 2 directions, you use the other 2 points. So that's another way to do it. Okay, so take your pick. Okay, so I guess we'll replace this.
Yes.
Right?
So the next one is that one over there.
Okay.
On the door.
Okay, so how about I start going through this question whilst
Yep.
Daniel's wiping through. Okay, so what's this question looking at? We have 3 points, A, B, and C, and we want to compute cross product of 2 of these displacement vectors A, B, and AC, and also look at the area of the triangle ABC. Okay, so this area is a typical application of the cross product, and it is pretty straightforward sort of a question once you know how to do it. Okay, so let's do part 1 and work out these displacement vectors first. Okay, so what's AB? So remember, just take the difference of these 2 coordinate vectors, 3, 4, 1, minus 1, 2, 3, and that equals 3 minus 1 is 2, 4 minus 2 is 2, 1 minus 3 is minus 2. And then AC, is, and you do the coordinates of C minus those of A, 3, 3, 4, minus 1, 2, 3. Okay, 3 minus 1 is 2, 3 minus 2 is 1, 4 minus 3 is 1. Okay, and the next part is the cross product. And this is just a formula, you have to remember it, okay? So it's a little bit complicated, but hopefully it's not too difficult. Okay, so the easiest way to remember it, the way we teach it, and there are lots of different ways, but this is the way we teach it. You look at the following 3 by 3 determinant with E1, E2, and E3. On the first row, the coordinates of the first one, A, B. In the second row, 2, 2, minus 2. And the coordinates of the second vector here as the third row, 2, 1, 1. Okay, so what's that mean? Okay, so let's just remind ourselves. So basically you have you expand along the top row. Okay, so you go along each of these, and basically you have some 2 by 2 determinant times each of these, and take that alternating sum. Okay, so you have some 2 by 2 determinant times E1, minus some 2 by 2 determinant times some E2, and then you have plus some 2 by 2 determinant times E3. Okay, so you just have to remember what these 3 2 by 2 determinants are. Okay, so for the coefficient of E1, so to speak, you remove the row containing those E's and the column containing that E1. So it's this one here. 2 minus 2, 1, 1. 2 minus 2, 1, 1. This one, remember there's a minus sign here. You do the same thing. You remove the first row and the middle column. So you get 2 minus 2, 2, 1. 2 minus 2, 2, 1. Okay. And then for the last one, which is the coefficient of E3, you just remove that last column in the first row. 2, 2, 2, 1. 2, 2, 2, 1. Okay. So let's keep going and work out what these 2 by 2 determinants are. So let's keep going. So remember how these 2 by 2 determinants work. You look at the product of the diagonal entries, so that's these two, and you subtract the product of the off-diagonal ones. So that's going to be, and I'll also write down what E1 is if you've forgotten. So it's 2 times 1, that's 2. And then minus the product here, minus negative 2. And E1, so these are the standard basis vectors in R3. E1 just means you have a 1 in the first position and zeros elsewhere. Okay? And now we do the same thing for the second one. This 2 by 2 determinant is 2 times 1, which is 2, minus the product of these two, minus 4. And E2 is just 0, 1, 0. And then the last thing you have is this 2 by 2 determinant here. So that's plus. The product here is 2. And then you subtract 2 times 2, which is 4. 0, 0, 1. Okay, so let's see what we've got. 2 minus negative 2. 2 plus 2 is 4. So you've got 4 times this vector, which is 4, 0, 0. And then you have to subtract 2 minus, so that's a plus 4. 2 plus 4 is 6. 6 times this, 0, 6, 0. And then you have to add in, I guess, minus 2. That's what this is, 0, 0, 1. And then we're almost there, okay? I guess the minus 2 should have gone in there, but it's quite easy to add these up. In the first coordinate, you just get the 4 here. So note there was zeros from these two because these had zeros in E2 and E3 in the first coordinate. So there's 4 here, there's a minus 6. And then here you've got minus 2 in the bottom. Okay? So remember this is a cross product of vectors. It's a vector product, so you put in 3 vectors and it spits out a 3 vector for you like that. Okay? So that's the operation of how you do a cross product, and of course, how is it useful? It's useful in answering questions such as this one here. Okay, so this one asks for the area of the triangle ABC. So let me just erase this bit and show you how that works. Okay, so that's rather nice. Okay, So the thing to remember here is that this cross product is a vector, and so being a vector has a magnitude and a direction. And both of those are useful in this course and in mathematics in general and also in physics. The direction is perpendicular to both the vectors that are factors. We won't use that part, we'll use the magnitude, and the magnitude in this case, so let me just draw the A, B and C. So we want to know the area of this triangle, and we've looked at vectors AB cross AC, and the magnitude of the cross product is just the area of the parallelogram with sides AB and AC. So that tells you how to work out the area of this triangle. Okay, so the area of triangle ABC equals half the area of this parallelogram, because of course these two triangles are congruent. Okay, so this is a parallelogram, half area of the parallelogram, sides AB and AC. Okay, and as I said, the magnitude of the cross product gives you this term here. So it's half times the magnitude of AB cross AC. And we just work that out over here. That's this one here, 4 minus 6 minus 2. So it equals half the length of 4 minus 6 minus 2. And I don't have a calculator with me here, so it's a little bit harder to work out. So I'll just slip the half inside. Okay. Remember, if you scale a vector by a scalar, it changes the length by that scale. So this is equal to the length of also of 2 minus 3 minus 1. Okay? And so how do you find the length of a vector? Remember, it's the formula is suggested by Pythagoras' theorem. You just look at the square root of the sum of squares. Okay, so it's 2 squared plus minus 3 squared plus minus 1 squared. Now the number's a little bit smaller for me, and it should just fit here what the answer is. Okay, 4 plus 9, 13, 13 and 1, 14. Okay, so there's the answer here, the square root of 14. And that gives you the area of triangle ABC using the cross product. It's a pretty useful gadget. Yeah.
Yeah, very nice. So we could have checked the normal. We could have checked this was in fact normal to the vectors just using that dot product thing we've already done, so we won't do that again, but you should get in the habit of just quickly doing a mental check, even with just one of the vectors, to make sure that all these calculations have in fact worked out as hoped for, because you're really pinning a lot on performing this arithmetic correctly, so it's worth just taking a moment to make sure that that's right. I might show you just a different way of doing the determinant. Believe it or not, this is the way that computing the cross product. Believe it or not, this is the preferred way of computing the cross product, but some of you haven't seen determinants yet. So I might just do a quick calculation to show how a kind of more naive way of doing it, although in a few weeks you'll all be doing it with determinants.
I guess just before you erase, always remember in the formula there's a minus which goes with the E2. Most students lose that 1 mark. That's always worth a mark to have that minus sign there, so don't lose that mark.
Good. So you have to remember some kind of device to compute the cross product. Here's one you might like. So here's the first line of it. It's that times that minus that times that. But then you need to remember what goes elsewhere. And the way you remember that is you just cycle through the numbers 1, 2, 3, 4. So the permutation is 1 goes to 2, 2's go to 3, and 3's go back to 1. So for the next line here, this is a 2, it goes to 3. And it's A3, B1 minus B3, A1. And then we cycle through this permutation one more time to get this entry, which is A1, B2 minus B1, A2. And in this way you can compute cross products. So we were given 2, 2 minus 2 cross.
Let's see whether I got the answer right now.
You did.
It's too easy to make a mistake in this game.
So it's this times this, so 2 minus this times this, minus 2. And then for the next entry it's A3, B1, so that's minus 2, minus B3, A1. So minus 4, minus 2. And then the final entry is 2 minus 4. So that's 4 minus 6 minus 2, which is what Daniel got. So
It's got to be right.
This is another. If 2 Daniels got the same normal, then it must be right. This is just an alternative way of doing it, and if you're down with the way Daniel did it before with the determinants, then great, because that's the way you'll always end up doing it. This is just something that's useful until you learn determinants.
So yeah, I guess we'll do more determinants later. So sooner or later, you have to get used to the definition and the way that I did it. Just something, if you find it hard to rotate things around, so you just cycle around like this. You put the A1 down here, the A2 down here, the B1 here, and the B2 down here. And then I guess the next ones are just A3, B1, B3, A1, and then you keep going. A1, B2, B1, A2. So if it's easier than doing it that way, you can just repeat them in the cycle like that, and it's just the same form all the way down.
That's nice. I didn't know that. Cool. I learned something today. Awesome.
Okay, great. Okay, we're on to question 4. I'll do the erasing.
Oh, cool.
And then you can read.
I can draw.
Yeah, you can.
Okay, so I've got the projection question, which is awesome. So we're given a point, we're given a line in parametric vector form, or almost in parametric vector form. We're told P is on the line, it's got this direction, and here's some Q floating out somewhere else. We're asked to find projection onto V of this, which is, okay, just a vanilla projection question.
I'll grab that.
But then we're asked to find the shortest distance between the line and the point Q. And this is really leading us directly into here. And I'll draw a picture first just to kind of show you where all these bits first fall. And I've added an extra bit. Sometimes the questions actually ask you to find the point Q. So I've added that in there just for fun. Cool,
Okay,
thank you. So the first thing I'm going to do, and the first thing I recommend you do, is just do a sketch for this. All the projection questions have the same sketch, but it will help you to kind of put these objects in their right places. So here's a line, here's a point, we're calling it P this time. 1, 2, 3. And here's some point Q floating out in space. Q, 1, 4, 4. And here's V. And what the projection always does is, well, the projection of PQ is PQ. The projection of PQ onto V gives you this vector, which I'll draw in purple. Here. So here's the picture that will help you with will help you put this question into something that you can solve with algebra. Here's some generic point, your line, and this purple vector is the projection, and this is a right angle in here. Great. So now let's actually do the question. Find the projection P onto V of PQ. Well, the first thing we need is PQ. PQ is the vector Q minus P, so this is 0, 4 minus 2 is 2, and 4 minus 3 is 1. Good. So for part I, this is the definition of projection, and the way it's got a bunch of V's and PQs in it, and I think it's important just to make sure you've got the right mix. This is a scalar. PQ dot V is a scalar. This length here, V squared, is a scalar. So whatever this is, it's going to be a scalar multiple of V. And you should check on your picture that your projection is in fact a scalar multiple of your direction vector. So just it's an easy thing to check just to make sure you've got everything in the right spot. And now we go forth and we actually compute some things. So we know what PQ is, and we know what V is. The length of V squared is the squared sum of these components, so that's 2 squared plus 1 squared in the direction of V. So that's 0 plus 6 plus 1 divided by 4 plus 9 is 13, 14. Which is just half of 2, 3, 1. So my purple vector is in fact half of my orange vector. Maybe I'll cheat a little bit just to promote my diagram to something that is roughly on scale. There we go. The purple vector is half the orange vector. Good. So that's part I. The second part is then to find the shortest distance between the line L and Q. Now you've got some options here. The vanilla option is to use Pythagoras' theorem. You know, you're after this squared and you've got PQ, you've got this purple vector, you could just do this squared minus this squared is equal to this squared, and that's exactly what we'll do. So, do we have a name for this point? No.
Yeah,
let's name it.
New name, yeah.
Let's name it. Let's R. Let's be unimaginative here. Didn't we hang on Q? Find
is the point.
No, I've written the question down wrong. We need to find R. Find R. But I haven't even introduced R. Let R be the point.
The bonus question also tells you which is the best way to do question 2, actually, part 2.
You think so?
Yeah, I think so.
I actually agree, but I see it done sometimes this way as well. Let R be the point of line closest to Q. Then, let's see, QR squared is equal to, QR squared is PQ squared minus PR squared, which is equal to PQ squared. Well, that's just 4 plus 1, which is 5, minus PR squared. That's, I have to work for this. That's, damn, 1/4, 4 plus 9 plus 1 is 14, which is, okay, so that's 7 on 2. 5 minus, okay, so that's, what is that? 3 on 2.
Looking good.
So, yep, okay. And
Looking
so
good.
length QR is √3/2. Okay. And bonus question is to actually go forth and find R. Well, to find R, and this is, to find R, well, we need to get there somehow. One way to do it is to take the vector, well, there's 2 ways you can go about this. the easiest way is to probably just go first from the origin to P, and then from P, and then PR. So let's do that. Maybe I'll keep that there just in case I need it. So for question 3, so OR is equal to OP plus PR. First I go from the origin, maybe there's an origin over here. I go the origin to P and then P to R, and I know what all these objects are. So that's OP plus PR which is equal to 1, 2, 2 plus 3 halves is 2 plus 3 halves, 3 and a half, and 3 plus 1 half is 3 and a half. So there's R for us. Good.
Great. Very nice solution. I like the way you put up a nice diagram here. This can get very confusing quickly. Okay, so to keep straight all your points and things like that, always have your diagram in there. And the other thing to note, as usual, when you want to work out coordinates of a point, it's often easiest to write it as the displacement vector from the reference point O to R. So when you write it down like that, OR, then it's very easy, even if you don't have the picture with you, to see the formula for OR. Of course, it's OP to plus PR. Okay, you can easily add these together, just purely algebraically, and you won't get lost that way. Great.
Good. Next question.
Okay, on to the next one.
Daniel, do you want to grab?
We'll grab the new sheet.
Oh, yep.
This is a long one. Did you write this question, Daniel? Did you write this test?
No, I didn't write this one.
This was how many years back? 3 years back. Okay, so what's happening in this question here? It's always good to draw a diagram when you start to get lost. Okay, that's what I suggest as you read these questions, and you just draw a diagram of each of the points and the lines as you read them. So a triangle. So I guess we need 3 points. What about O, A, and B? So we've got O somewhere here, 0, 0, 0, A, and B. So A is 4 minus 4, 8, and we can put in that triangle. And what else do we have? Another point here, X. X be a point on OA. So it's on here, such that OX is 3/4 of OA. So OX is just going to be 3/4 the length of this one here, okay? So maybe it's about here. Is our X, okay? And Y is a point on OB, such that OY equals 2/3 OB. So you want it to be 2/3 of this here, 2/3 of the way, Y. So I guess the ratio here is 3 to 1, 3 to 1, and this is 2 to 1. Okay, so what does it ask for? It asks for some parametric vector equations, in this case of 2 lines, AY and OB, and show they intersect at this point here. Okay, so let's just do each of these lines separately, AY and OB. Okay. AY and OB. Is that meant to be an XB? You might want to check if that's supposed to be an XB.
Yes, it is supposed to be XB.
Yeah,
Thank
I
you.
think it's got to be an XB. Okay, so let's try that with an XB and see if we get it right. Okay, so let's do AY first. So that's this one here. And we want to see it intersecting with XB. And it's supposed to be at this point, P. Is that the point of intersection? This one here. Okay, so let's see line AY. Okay, so we've got the point A. Well, let's work out the coordinates of Y and X first. So what are the coordinates of X? So we can write that as OX equals, well, it's 3/4 of the length of OA. So it's just 3/4 OA. Okay, so that's 3/4 of, well, A was 4 minus 4, 8. 4 minus 4, 8. So that's equal to, divide all these by 4, 1 minus 1, 2, multiply by 3, so that's 3 minus 3, 6. That's what it looks like to me. Okay, 3 minus 3, 6. Okay, so that gives you the coordinates of x, right? OX, that displacement vector is the coordinates of x, and y you work out similarly. So let's just do that quickly. OY equals 2/3 of OB. B was 0 minus 3 minus 6, minus 3 minus 6. So when you multiply that by 2/3, 0 here, of course. 1/3 of this is minus 1 times 2 is minus 2. 1/3 of this is minus 2 times 2 is minus 4. Okay, so there are your points. And now we want the parametric vector forms of AY and XB. So let's put them in. I'll need to have a little bit more board space in a little while. Let me just work out AX, so no, AY, that's the first one, isn't it? AY, line AY. Okay, so you just pick a point here. That's may as well be A. So X tilde equals A plus lambda V. And what you need is a point. We've got 2 points. And we also need the direction. So the direction, I guess, is, so here, V is equal to, say, the displacement vector AY. That will do, or YA. Let's just pick AY. So what were the coordinates of Y? They're here. 0, minus 2, minus 4. And the coordinates of A were 4 minus 4, 8. 4 minus 4, 8. Okay, so let's just work out that out. 0 minus 4 is minus 4. Minus 2 minus 4 is minus 6. No, I don't think that's right. Let's try again with that one. I just need to erase this. So that's going to be somewhere. Where did I put it? Okay, good. So minus 2 minus negative 4 is, add 4 to that, that's 2. And then 8 minus 4 minus 8 is minus 12. Okay, so that's direction B. So X equals A, you might as well pick to be the A here. So that's the A. 4 minus 4, 8. And then you have to add lambda times this vector here. Minus 4, 2, minus 12. Okay? And you can do the same thing with the line XB. Okay, so for the line XB, you just have to work out the direction, similarly, and pick a point where you've got the 2 points there anyway. So the direction is, let's do BX. So that's the coordinates of X, 3 minus 3, 6. 3 minus 3, 6. And then you have to subtract from that the coordinates of B, which is over there, 0 minus 3 minus 6. Okay, so just do the subtraction. 3 minus 0 is 3. Minus 3 minus negative 3, they're the same, so it's 0. And 6 minus negative 6, so that's 12. So just some things that if you want, you can do to simplify the calculations. Remember, you can pick any direction vector. So if you want to simplify your algebra, you can divide this by 3. It's a parallel vector, so the direction is the same. Or 1, 0 divided by 3 gives you 4. Okay? So now you can write down the parametric form. So it's going to be the vector B over here. 0 minus 3 minus 6 plus lambda, this direction vector, 1, 0, 4. Okay, so we've got both of these. And then that's the first part of the question, is to find the parametric vector equations. Okay, as usual, I guess you should, you can check your answer, and I guess in this case, maybe there's no other way than to repeat the calculation that we've got in here. That's the best thing. Okay, so let's do the second part, which is to show that they intersect at this point here. And I guess there are two ways you can do that. Either you can try to intersect these two, okay? And usually intersecting lines like this isn't so easy. So the first thing you should do if you intersect the lines is actually you should put, firstly, these parameters, they range over all of the reals. And if you want to intersect them, you better give this parameter a different name, maybe mu, and then solve simultaneously. Okay. But the other way that you can do this is just check the point P is actually on both these lines. Okay, so let's do it that way. Okay. So let's check if P is on them. That's the next part. So if P happens to be on both those lines, well then it must be the point of intersection. As they're lines in R3, they intersect, and they're distinct lines too. They're not parallel, okay? So they're distinct lines, so either they don't intersect or they intersect in at most one point. Okay, let's see whether this intersection, they do intersect, and they do intersect in 2 minus 3, 2. Okay, so so you can write down is P on AY. Okay, so we're going to check whether this point has this form. So we solve. 2 minus 3, 2 is equal to 4 minus 4, 8 plus lambda minus 4, 2 minus 12. Okay, subtract this from both sides. Okay, so therefore this is the same equation as equivalent to subtract 4 from 4 minus 4, 8 from both sides, minus 2. Subtracting minus 4 is adding 4, that's 1. And then subtracting 8 is minus 6 equals lambda minus 4, 2 minus 12. And can we solve for this? Well, you have to find the lambda, solving for lambda here. And it looks like to me lambda equals half. Lambda equals half works. Okay, half of minus 4 is minus 2, half of 2 is 1, half of minus 12 is minus 6. Okay, so you can just eyeball that one and see that straight away. Okay, so at least P is on this line, okay? And let's just see whether it's on this line as well, okay? And then we'll have our answer. Okay, so is P on BX? Okay, we do the same thing. We'll solve 2 minus 3, 2 is equal to, now we have this, what's the 0 minus 3 minus 6 plus lambda 1, 0, 4. Okay, so we subtract this vector from both sides. Okay, so we get rid of that, and we just have the lambda here. So we get 2 minus 3 minus negative 3 is 0. 2 minus negative 6 is 8 equals lambda 1, 0, 4. And can we solve this? Yeah. Okay, so lambda equals 2 here. So lambda equals 2 works. So what's that imply? P is on both AY and BX. So these lines intersect at P. Okay? And that gives you the answer to this second part of the question here. Okay, so remember, it's always good idea. Make sure you answer the question that's given to you. Sometimes you do so much calculations you forget why you're doing them. Okay, so it asks you, do they show they intersect? And so repeat that you've shown that they've intersect. So P is on both of them. That's what you showed here, and hence these lines intersect at P.
It's a nice answer. I especially like how Daniel showed P was on this line, and then as a separate calculation showed P was on this line. It's P because we know it, it's kind of easier to show it this way. You can actually solve it by substituting, just equating this line with this line, called lambda 1, say this is lambda 1, lambda 2, and actually work out the values of lambda that way. You can do that. The question's been crafted so you could actually perform that calculation. I kind of prefer this because it shows that P is common to both these lines. Good. Good answer. All right.
Okay, great.
Last question. What do you want?
Yeah, I'll do the honors.
Okay. Good. Okay, so I chose this because it was a kind of wordy question, and wordy questions scare people. So here's a question. You have to apply you have to read it and then apply your understanding of algebra. First place, drawing. Always do a drawing. So let's write down a parallelogram. OABC is a parallelogram. I think I meant to write it as OCB like this. So this is the parallelogram like that. There's the origin, A, C, B like this. So this is the vector, let's call it A. This is the vector, let's call it B. And this is the object we're interested in. Question 1, write down parametric vector equations for the lines OC and AB in terms of vector A and vector B. Okay. This is not so bad. The line through, well, the line through here. Well, first of all, how can we express C? C is just vector A plus vector B because it's a parallelogram. So since OC, I can write that as just A plus B. Then the line through O and C is as follows. You need to pick a point on the line and the direction of the line. Let's call this one line OC is x is equal to point on the line. I'll just choose the origin. So the 0 vector plus lambda 1 times the direction of this line is just going from O to C. So I'll just choose A plus B. Like that. And if I want the line from, so that's this line going from 0 to C. And for the other line from between these two things, I need to, well, how can I construct this? Let's choose this as my point on the line and then this direction, AB, as my direction vector. It's X. I'll choose A as my point for the coordinate vector of a point on the line plus lambda 2 times this direction vector, AB. So that's just B minus A. These are my parametric vector equations for the line, the two lines. Now the tricky bit. Find the coordinates of the point P, which lies at the intersection of OC and AB. So that's this point here, P. And these are two lines. I can't just look at the coordinates of P and find the lambdas. I need to actually equate these two things. So that's what I'll do. I have no choice. I'll write this as say 0 plus lambda 1 A plus B is equal, so this is part 2 now, is equal to vector A plus lambda 2 B minus A. Good. And now what I'm going to do is I'm going to shift all the A's onto one side and all the B's onto the other side. So here's some B's. I've got lambda 1 plus lambda 2, no, lambda 1 minus lambda 2. Times b, and that's supposed to be equal to 1 minus lambda 1 plus lambda 2 times a. So how many? I shift lambda 1a over there, and I get 1 minus lambda 1 minus lambda 2. And now I use the fact that a and b are not parallel. See, what this is saying is that a multiple of b is equal to a multiple of a. But a and b aren't multiples of each other by this property. And the only way I can then make this work is if this is 0. See, a cannot be equal to lambda b. You can't have one of these things as a scalar multiple of the others. So this thing is equal to 0. So this has to be 0, and this also has to be 0. This one implies that lambda 1 is equal to lambda 2, and 1 minus lambda 1 minus lambda 2 is equal to 0, but lambda 1 is lambda 2, so this is like saying 1 minus 2 lambda 1 is equal to 0, so lambda 1 is equal to 1/2, which is equal to lambda 2. So lambda 1 and lambda 2 are both 1/2. Well, so how do I get to P? I can just traverse my line OC, and I substitute in lambda 1. Lambda 1 is equal to half. OP is equal to the 0 vector plus 1/2 A plus B, which is, well, just half A plus B.
I like this solution. It's also easy, I guess, to check that P is on the other line too, right?
The P is on both these lines.
On AB as well.
Oh
right?
yeah, you could just substitute it at half.
Yeah.
Absolutely.
Lambda 2 equals half. So you get half B here, and then minus half A from that A, that's half A. Yeah, that's great.
This is
Nice
where
and clean.
this is where all the work is, by the way. The rest of it is just a kind of trivial calculation where you calculate some lengths. So P, I guess we'll add OP. And then we need to show OP is length PC. Well, for part 3, what is PC? PC is C minus P, so that's the C is A plus B minus OP. Well, maybe I write this as OC minus OP, which is A plus B minus 1/2 A plus B, which is A plus B minus half A plus B. It's just again half A plus B. And in fact, that is OP. So of course, if these are in fact just the same vector, then the length PC must also be equal to the length OP. And we perform the same calculation, but this time with the other diagonal. We just have to calculate what PA is and PB. PA is OA minus OP, which is A minus, which is, now it's going to be half A minus a half B. And let's go. Well, the question actually asked PB, so let's do that. PB is OB minus OP, which is B minus let's say it's negative A minus B. So therefore PA, which is equal to length is also equal to the length of the negative of this, which is length PB. Which is what the question asks us. So this is just kind of routine stuff at this point. Once you have P, you just have to calculate some lengths. So that's not too hard. But the hard bit is showing that that is the intersection. And you could probably guess that P is going to be the midpoint of this anyway. So that kind of confirms for you your intuition about parallelograms. Daniel.
That's a nice clean solution, Daniel. Yeah, of course, what is this fact? This hopefully is a fact you know from high school geometry, and that is that the diagonals of a parallelogram, they bisect each other. So they intersect each other. How? In such a way that they cut each of the diagonals in half. So that's a nice thing. I think that a lot of students, they find it a little bit tricky just because if you actually had vectors for A and B, like 1, 2, 3 or 2, 3, 4, usually students find it's fairly easy to do. But yeah, when you have abstract things like that, you just have to be clear that they just stand for something like 0, 1, 2 or whatever, some vector, but you just leave it written as A. And often, as a result, when you write out the answer, it comes out quite cleanly like that.
Good. So good luck with your tests. Please remember to start your questions with a picture. That's just blanket good advice. Daniel, do you have one piece of blanket good advice for everybody?
Yeah, do check your answer if you can. And remember that there are tutors available throughout the week to help you out if you need any help, some face-to-face contact time.
Good. All right. Good luck and thank you.
Good luck.